Okay, welcome to today's lectures. We're going to be looking at homogeneous differential equations. So I'm pleased to introduce homogeneous differential equations. It look tough, perhaps if you've seen it before, but trust me, you're going to understand the background of homogeneous differential equations. Now, let's dive into homogeneous differential equations. The general form of the homogeneous differential equation can be written as f of x comma y plus g of x comma y dy dx equal to 0. So what are f of x comma y and g of x comma y? So they are assumed to be homogeneous functions. Of course, that's why we call it a homogeneous differential equation. So because they are homogeneous functions, first of all, the criteria to call them homogeneous functions is that they have to satisfy this rule over here, that for some non-zero constant lambda, when you substitute x for lambda x and y for lambda y, you're going to obtain lambda raised to the power of n f of x comma y. And the same thing happens to g. If you substitute x for lambda x and y for lambda y, you're going to obtain lambda raised to the power of n g of x comma y. So this might sound bizarre and totally new or vague to your understanding, but trust me, you will understand it. You will get to understand it. Okay, so this is just like the test for homogeneity, test for homogeneous differential equation. So, and this is how we write the test. Now, for a differential equation that is non-separable, okay, for differential equation that is non-separable, that means anytime that we cannot apply method of separable variables or linear technique with our integration factor, then if at all this is going to be a homogeneous differential equation, then it has to satisfy this particular axiom that is stated in this particular line. Now, a homogeneous differential equation is always classified according to its degree, okay, and it is n. So where did we get n from? N is actually gotten. Now, after you substitute x for lambda x and y for lambda y, and after you factor out whatever you get here in this particular position, it becomes the degree of that homogeneous differential equation, and it is read as a homogeneous differential equation in degree n. So you might hear someone say homogeneous differential equation of degree 1, degree 2, degree 3, and so on and so forth. Then a homogeneous differential equation have no constant term or special functions, sine, cosine, logarithmic, exponential, inverse trigonometric functions, or inverse logarithmic functions, or whatever, what have you, no special functions. So we just have only polynomials basically, and there is no constant term. A homogeneous differential equation cannot have a constant term. Okay, so take note of that. So with no constant term, okay, just like we emphasized here. So there is no constant term, there is no special functions, so you just have the ratio of some polynomials in terms of x and in terms of y. Okay, so we'll get to see an example later on. Now, a homogeneous differential equation could be written in form of a sword. That means with square root symbols. Okay, as far as I know, we can write a homogeneous differential equation with square root symbols. Now, maybe to just demonstrate what this looks like, assuming I gave you something like this: dy dx is equal to the square root of 2x squared minus y squared over xy. Now, we'll get to discover later, and I'll let you prove later on your own, that something like this is actually a homogeneous differential equation. So we can actually write it in terms of a sword in this form. So maybe later on we'll solve something like this in the future, so anticipate to know how to solve something like this. So let's go on to say more about homogeneous differential equations. So a homogeneous differential equation of degree n can actually be known by understanding this particular rule here. Now, the total sum of the powers, whether from mixed or from unique variables in each term, must be equal to n. I'm going to explain this with a demonstration, okay, so that you can understand it. let's jump down to the last point for today. So the key to solving homogeneous differential equation is to make the substitution y is equal to vx, where v is a function of x. So if v is a function of x, y equal to vx, then dy dx should be v plus x dv dx, and v is equal to y over x. So it makes sense. So you have y is equal to vx. Of course, when you differentiate, since v is a function of x, you have to apply product rule. Differentiating x, you have 1, then you keep v. Okay, well, let me just put it 1. And you differentiate v, then you keep x. So you can rearrange to get your v plus x dv dx. Alright, so since of course y is equal to vx, v can be made the subject of the formula, so that anytime we see v, we can replace it with y over x. Now these are the principal substitutions that we have to make in order to solve our homogeneous differential equation. Okay, so there are stages where we are going to be making this substitution. Like this one, you make this substitution, this first two, 1 and 2, you make it at the beginning of your solution. Then this one, you make it at the end. So end, beginning, beginning. Okay, so this first two will be made at the beginning, then this one will be made at the end of your solution. So we are going to see an example. Now, just to stress more on this particular rule, how do I know a homogeneous differential equation? I'm just going to give an example. Now, with a random homogeneous differential equation from my mind, you have dy by dx is equal to x cubed plus 3xy squared all over 3x squared y plus y cubed. Alright, so this is some random differential equation. First of all, let's test for homogeneity. So test for homogeneity. So we want to say that this differential equation is in this form: f of x comma y over g of x comma y. So I can test the numerator if the numerator is a homogeneous function, and of course can be able to make some assumptions from the denominator from other things that we've learned so far. So we have our f of x comma y from the numerator to be x cubed plus 3xy squared. So the rule said that we should substitute x for lambda x and y for lambda y. Okay, so when we make the substitution, anywhere we see x, we're going to get what? Lambda x whole cube plus 3 lambda x, then lambda y. Anywhere you see y, you put lambda y. So you're going to get lambda cube x cube plus 3 lambda x lambda square y squared, like this, and this is lambda 3x cube plus 3 lambda cube x y squared. Is that okay? So this is our f of x, lambda x comma lambda y. And if you factor out lambda cube, you're going to have x cube plus 3xy squared. This is my f of lambda x comma lambda y, and this is actually lambda cube f of x comma y. So this whole term is our f of x comma y. So it actually passed the test. Okay, the numerator passed the test, and now before I solve for the denominator, of course I know the denominator will pass the test, but we can actually use this particular axiom now to also know that it's going to be a homogeneous differential equation. They said the total sum of powers from mixed or unique variables in each term must be equal to n. Now we've already gotten n, right? We said that anytime we finish solving for lambda and we factor out what? Lambda, whatever is here is going to be n. So n in this case is equal to 3. Now look at this homogeneous, or look at this differential equation. not assume it's homogeneous right away. We're actually determining whether it's homogeneous or not. It has 4 terms, 2 terms in the numerator and 2 terms in the denominator. So term 1, term 2, term 3, term 4, like this. Now term 1 is a unique term, okay, and term 2 is actually mixed with s and y. Term 3 is mixed with x and y, and term 4 is unique in terms of y. Term 1 is unique in terms of x. Now what is the power of term 1? So power of term 1, total power in term 1, the total power is 3. So total power in term 2, of course, is a mixed term. So x has 1 and y has 2, so 1 plus 2 is 3. So total power in term 3, okay, total power in term 3, you have that term 3, for term 3 you can see that x is 2 and y is 1, so it's also 2 plus 1, 3. And total power in term 4, you can see that of course it's a unique term, not mixed, and y has a power of 3, so it's actually 3. Now all the terms have unique powers, hence it is homogeneous in degree 3. So this is degree 3 homogeneous differential equation. Now as for the other one I came up with, the dummy one, like a sword, let me say 2y squared minus x squared all over x y. So I want you on your own to actually try to prove, or let me say, is this 2y4? Let me make it 2y4, something like this. I want you on your own to check if it's going to be homogeneous. So let me make a correction on this side, 2y4, like this. I want you on your own to check if it's going to be homogeneous, okay? So you can try to make it homogeneous by yourself, or to try to check if it's going to be homogeneous by substituting on the numerator and the denominator lambda x, and I want you to determine the degree. So you can post your answers on the comment section for this particular case, and I'm going to let you know if you're correct or not. I'll also share a solution for this kind of problem much later in the video. So thank you for watching the introduction to homogeneous differential equations. In next class we're going to begin with solving the following questions. We're going to solve the following problems and see how to get their solutions. So these are problems extracted from questions that are homogeneous in nature. So we'll learn how to solve each and every one of them, and I believe that after solving them your hands are going to be strong in approaching homogeneous differential equations. So thank you for watching today's video. Do like and subscribe and hit the notification button to stay updated. Share to your friends too, and anticipate the next video. So take good care of yourself, keep your hands hot by solving, don't stop solving, keep solving. Okay, see you in the next video.